Light knows you're watching it. I'm serious. Send a photon through two slits, and it behaves one way. Try to catch it in the act. See which slit it actually went through, and it does something completely different. The pattern on the detector changes the instant you decide to look. Not because the measurement equipment is clumsy. Not because you bumped something. The universe itself responds to whether or not you're paying attention. And I'm going to show you exactly why this isn't mysticism, isn't philosophy, and isn't up for debate. It's what actually happens. Here's what we're going to do. We'll fire electrons at a screen with two slits cut into it, one at a time, slow enough that only a single electron exists in the apparatus at any moment. Behind the slits, we've got a detector that registers where each electron hits. Simple setup, clean experiment. Now watch what happens. The first electron hits, just a dot. Random location. Second electron hits somewhere else, another dot. Seemingly random. Third, fourth, fifth. Dots appearing in no obvious pattern. You're watching this and thinking, okay, particles going through slits, bouncing around, landing wherever. Makes sense, but keep watching. 10th electron, 20th, 50th. Something strange starts emerging. The dots aren't random anymore. They're forming stripes, bright bands where lots of electrons hit, dark bands where almost none hit. By the time you've sent through a few thousand electrons, the pattern is unmistakable. Interference stripes, the signature of waves. But here's what should break your brain about this. Each electron went through alone. There was nothing for it to interfere with. The previous electron was already detected and gone. The next one hasn't been fired yet. So what interfered with what? You're staring at wave behavior from particles arriving one by one. Let me make this concrete. When water waves pass through two openings, they spread out on the other side. Where the peaks from both openings meet, you get a bigger wave. Where a peak meets a trough, they cancel out. That's interference. That's why you get alternating bands of high and low intensity. But water is continuous. It's actually going through both openings simultaneously. The electron is a discrete particle. It's a single lump of matter. How can one particle interfere with itself? So you propose something reasonable. Maybe the electron splits somehow. Maybe part of it goes through one slit and part through the other, and the parts interfere. Or maybe the electron goes through one slit, but there's some kind of influence or pilot wave that goes through both, and that creates the interference. These aren't crazy ideas. They're exactly what any sensible person would think. Let's test them. We modify the experiment. We put detectors right at the slits, tiny detectors that can tell us which slit the electron went through. We don't touch the electron, don't deflect it, don't do anything that would obviously disturb it. We just watch. Now we fire electrons again, one at a time, same as before. And this time, every single time an electron reaches the detector at the back, we see a flash at one of the slits. Slit 1 or slit 2, never both. The electron definitely went through one slit or the other, not both, not split between them. One definite path. So you've answered the question. The electron goes through one slit. Good. Now look at the pattern building up on the back detector. The stripes are gone completely. Now you've got two bright patches, one behind each slit. Exactly what you'd expect from particles taking definite paths. The interference pattern vanished the moment you determined which slit the electron used. Turn off the detectors at the slits. Don't look. Fire more electrons. The interference pattern comes back. Turn the detectors back on. Pattern disappears. On, off, on, off. The pattern appears and vanishes depending on whether you're checking which path the electron took. The electron somehow knows whether you're watching, and it behaves differently based on that knowledge. This isn't a flaw in the equipment. This has been done thousands of times with increasingly sophisticated apparatus. Electrons, photons, atoms, even molecules made of 60 carbon atoms. Same result every time. When you don't look at which path the particle takes, you get interference. When you do look, you don't. The act of measurement changes what happens. Now, most people hear this and immediately jump to something mystical. Consciousness creates reality. The observer collapses the wave function. The universe needs minds to exist. All of that is garbage. The word observer is misleading. It's got nothing to do with consciousness or minds or awareness. When I say observation, I mean physical interaction. The detectors at the slits work by bouncing photons off the electrons to determine their position. That interaction, that physical disturbance, is what changes the behavior. It's not about knowing, it's about doing. But here's what still bothers everyone, including me. Why does finding out which slit the electron went through destroy the interference? What's the connection between gaining that information and losing the pattern? That's where things get really strange. Let me try to make this clearer by thinking about what information actually means in this context. When the electron leaves the source, it's not a particle in the classical sense. It's described by something called a wave function, a mathematical object that contains all possible paths the electron could take, both slits simultaneously. The wave function literally passes through both openings, interferes with itself, and that interference determines where the electron is likely to land. But the moment you measure which slit it went through, you force the wave function to commit. You make it choose. The electron can no longer be in a superposition of going through both slits because you've extracted information that says it went through one particular slit. And once you know that, the mathematics changes completely. The interference terms vanish from the equations. They have to, because interference requires two paths, and you've just determined there was only one path. This isn't optional. This isn't some weird quirk we could engineer around. It's built into the structure of quantum mechanics itself. There's a fundamental relationship between what you can know about a quantum system and how that system behaves. They're not independent. Gaining information about the path destroys the ability of the paths to interfere. Now, here's something that makes this even more bizarre. You don't actually have to look at the measurement result. Set up your detectors at the slits, let them record which path each electron takes, but don't look at the data. Just store it somewhere. The interference pattern still disappears. The information exists. That's enough. It doesn't matter whether you personally know it or whether anyone knows it. What matters is whether the information is physically present in the universe, recorded somewhere, even if nobody ever reads it. Erase that information. Destroy the records before they can be correlated with where the electrons landed, and something remarkable happens. The interference pattern comes back, not because the electrons change their behavior retroactively, but because without that which path information, the universe treats the situation as if both paths were available. This has actually been done, by the way. Experiments in the late 1990s demonstrated exactly this effect using entangled photons. One photon goes through the slits. Its entangled partner carries which path information. If you measure the partner in a way that reveals the path, no interference. If you measure it in a way that erases the path information, interference returns. Same photons, same apparatus, different information available, different patterns. What does this tell us? It tells us that quantum mechanics isn't about particles following definite trajectories that we just happen to be ignorant of. If that were true, measuring the path would simply reveal information that was already there, like opening an envelope to read a letter that was written yesterday. The pattern would be the same whether you open the envelope or not. But that's not what happens. The act of making path information available changes the physical outcome. Not because of any physical disturbance in the crude sense of bumping into things, but because quantum systems exist in superpositions until something happens that forces them into definite states. Measurement is that something. Interaction with a detector is that something. Creating a permanent record is that something. You're probably thinking this is absurd. How can an electron know whether information about it exists somewhere? How can it adjust its behavior based on whether a record was kept? It can't, obviously. Electrons don't know anything. They don't think. They don't make decisions. What's really happening is that the electron isn't a little ball following a path. It's a quantum object described by a wave function, and that wave function evolves according to precise mathematical rules. When you set up detectors, you entangle the electron's wave function with the detector's wave function. That entanglement changes the mathematics. The interference terms that were there before are now somewhere else in the combined system, effectively invisible to the screen where you're looking for them. This is what quantum mechanics has been trying to tell us for a century. The world isn't made of little billiard balls bouncing around on definite trajectories. It's made of wave functions, probability amplitudes, quantum states that exist in superposition until something forces them to become definite. And that forcing, that transition from superposition to definite outcome, involves physical interaction, entanglement, the spreading of quantum information through the environment. We call this decoherence. The quantum system interacts with its surroundings, gets entangled with more and more particles, and the delicate superposition states that allow interference get scrambled into the environment. From our perspective, watching the system, it looks like the wave function collapsed, like the quantum behavior disappeared, but nothing disappeared. The quantum information just spread out into so many degrees of freedom that we can't track it anymore. This is the heart of quantum mechanics. Not mysticism, not consciousness, not philosophy, physics. Precise, mathematical, tested physics. And it's telling us something profound about reality. The world doesn't split into quantum and classical because of size or complexity. It splits because of entanglement with the environment. A single electron in perfect isolation behaves quantum mechanically, always. But perfect isolation doesn't exist outside carefully controlled experiments. The moment that electron interacts with anything, a stray photon, an air molecule, the thermal vibrations of the apparatus, it gets entangled. Its wave function doesn't exist in isolation anymore. It's correlated with the environment. And once you have billions of environmental degrees of freedom all entangled with your electron, recovering the interference pattern becomes impossible. Not because the quantum behavior disappeared, but because the information you'd need to see it is scattered across too many particles to ever collect. This is why you don't see quantum superposition in everyday life. It's not that large objects obey different laws. They don't. A baseball follows quantum mechanics just as much as an electron does. But a baseball is made of 10 to the 26th atoms, each one constantly interacting with air molecules, photons, everything around it. The entanglement with the environment happens so fast, so completely, that the quantum behavior gets washed out before you could ever hope to detect it. We call this the decoherence timescale. And for macroscopic objects in normal conditions, it's absurdly short. A speck of dust decoheres in 10 to the minus 31 seconds. You're not going to see interference patterns from that. Now here's something that bothers people. If decoherence explains why we see definite outcomes, why we don't see cats both alive and dead, then what about the environment itself? Doesn't it have a wave function? Doesn't the entire universe exist in superposition? And the answer, mathematically, is yes. The wave function of the universe, if you could write it down, contains all possible configurations superposed together. But that doesn't mean you see all of them. You're part of the universe. You're entangled with it. When you measure something, you don't stand outside the system looking in. You become correlated with the outcome. Your brain state, your memories, everything about you branches along with the result. Some people take this seriously. They say every measurement creates a branching of reality, and all outcomes happen in different branches. That's the many worlds interpretation. I'm not going to tell you whether it's right or wrong. I don't know. Nobody knows. What I can tell you is that the mathematics works, the predictions are correct, and everything we've tested agrees with the theory. Whether there's one world or many, whether the wave function is real or just a calculational tool, those are questions beyond what the equations tell us. What the equations do tell us is remarkable enough. They tell us that particles don't have definite positions until something forces them to. They tell us that measuring one property prevents you from simultaneously measuring another. They tell us that identical particles in quantum mechanics are truly identical, not just similar, and that has profound consequences for chemistry, for why matter is stable, for why you can't squeeze electrons into the same state. The Pauli exclusion principle, the thing that keeps electrons in different atomic orbitals, that's a quantum effect. Without it, all the electrons would collapse into the lowest energy state, and chemistry wouldn't exist. Neither would you. Feynman said, and I agree with him completely, that nobody understands quantum mechanics. Not really. We can use it, calculate with it, build technology from it. But understanding in the sense of having an intuitive grasp of why the world is this way? No. The math works. The experiments agree. That's all we've got. And honestly, that's enough. You want comfort? You're in the wrong field. You want truth? You accept that nature doesn't care about your intuitions. The double-slit experiment shows you everything. One experiment, endlessly repeatable, demonstrating wave-particle duality, superposition, measurement, decoherence, all of it. You can spend a lifetime thinking about what it means, and people have. Or you can accept that this is how the universe operates at its most fundamental level and move on to calculating what happens next. Either way, the electrons keep doing their thing, completely indifferent to your philosophical discomfort. So when someone asks me why quantum mechanics is the way it is, I tell them it's not a why question, it's a how question. How does the universe behave? Like this. We've measured it, we've tested it, we've built computers and lasers and nuclear reactors based on it. The universe is quantum mechanical. Deal with it. That's not arrogance. That's physics. And if you can handle that, if you can accept that reality doesn't match your inherited intuitions about how things should work, then you're ready to actually learn something real about the world. Look, I've shown you what happens when you actually do the experiment. Electrons behaving like waves when you're not looking, like particles when you are. The pattern appears and disappears based on whether path information exists. That's not opinion. That's measurement. And the moment you accept that, the moment you stop demanding the universe match your expectations and start asking what it actually does, you're doing physics. Everything else is just noise.